I think what has always excited human beings is the unknown. I mean, it's always the edge that we're working on, but there's also the idea of going where no one has gone before.
We remain in the dark about what makes up 96% of the universe. Join physics and astronomy professor Dr. Dinesh Loomba as he sheds some light on the dark matter phenomenon.
I think there's something about us as Americans and our American culture that we relate back to the Greeks and Romans in ways that are cultural, are political, sexual.
Why are the stories of the ancient world being told and retold in the movies? Classics professor Dr. Monica Serino discusses how the movies reconstruct the image of ancient Rome and the intersection between classics and popular culture in film and television.
Global warming is going to shake up bird distributions in all kinds of ways that are difficult to predict.
Dr. Christopher Witt, curator of birds at the Museum of Southwest Biology, answers the question, how will global warming affect hummingbirds? Welcome to Connect, where each month we connect with the great people and inspired thinking found at the University of New Mexico. Connect is next. Joining me now is Dr. Dinesh Loomba. Let's just jump right into this topic because we could probably talk about it for 2 hours straight. What is dark matter?
Well, that's the big question. You know, a lot of the research happening across the world right now has to do with what is its nature. First of all, what is it? In the sense that how do we know it's there? If it's dark matter, that means we don't see it.
So how do you describe it?
So how do we even begin to describe it? What is its nature? And then go and find out more about it. Find out its properties. You know, is it a new particle? Is it something completely different we haven't imagined? Something coming from an extra dimension, for instance, or string theory or something like that. So to answer the question, you know, what is it? First we have to take a step back and ask, how do we know it's there? If it's dark, we don't see it, how do we infer it's there?
And how do you look for something that in effect is
Right,
not there?
Right, exactly. So there's a lot of hints from nature, and most of these hints come from scales of galaxies and larger, and even going very far back into the early universe from the microwave background radiation. But if we begin with galaxies and we say there's so many stars inside a galaxy like our own, there's something like 10 billion stars, for instance, and then there's so much gas. And we add it all up and we use Newton's law, which says, you give me how much mass there is, and I'll put a star out near the edge of the galaxy, and I can tell you how its motion should go. How fast should it go, for instance, as a function of its distance from the center. And when we do that calculation, and we do the observations, we count up all the stars, all the mass inside the galaxy and stars, all the mass in the gas, everything that we see. The stars out near the edge of the galaxy are moving too fast. The gravitational pull due to all the mass in the galaxy is not enough to account for the motion of the stars out near the edge of the galaxy.
And so that's why we know.
That's why we think there is dark matter. Okay. So if we take a step back, this required a lot of assumptions, right? One was that I use Newton's laws. So how do I know that Newton's laws work on the scales of galaxies? How well has it been tested on the largest scales? We tested in the solar system. That's what Newton had done. He had proposed his law to explain how the planets move around the sun. And so if we observe each planet's motion and say that the mass in the solar system, most of it is right in the sun, it's 99% or more of the mass of the solar system, we see that the motion, the speeds of each of the planets as they move around the sun falls with a very particular nature, mathematical nature, given by Newton's law. Okay? So Pluto is moving very slowly, Mercury is moving very, very fast. And an example of the dark matter problem can be taken if we go back to when we only had something like 7 planets that we knew about. One of those planets was moving in a very peculiar way, not according to Newton's law. So at that early time, people said, okay, maybe Newton's law is wrong. It works 99% of the time, but here's one example where it doesn't work. So we'll just take that as it's an approximate law. Some other people came along and said, no, wait a minute. I've tested it so well. What if I make the following hypothesis, that it is correct? What is it trying to tell us? And what they said is maybe there's another planet out there that's perturbing the motion of Uranus. That was a planet that wasn't working quite according to Newton's laws. And they did the calculations. They said, okay, what mass should that planet be? Where should it be? And then they told their observatories, for instance, point there, you'll see another planet. One of the observatories looked at this person who was telling them to point there and said, you're just sitting there with a pencil and paper and using Newton's laws and you're going to waste my time. The other observatory said, okay, we'll look. And they did, and they found Neptune. So that, in effect, is like a dark matter problem. There was something dark there. We didn't see it. But it did influence something else. How did it influence it? Gravitationally. It had a little tug on Uranus, and so we discovered Neptune.
And so when you talk to students, K through 12, as you often do, Dinesh, how do you get them excited about something they can't see?
I think the students are naturally taken by mysteries. Okay, you can also tell them, you know, as we do in the university as well as K through 12, all the things we do know. But I think what has always excited human beings is the unknown. I mean, it's always the edge that we're working on. Many of us are working on things that are not necessarily the edge, but in deeper ways of things that we already know. How do they work? You know, going into tremendous detail of something which we have a rough idea about. But there's also the idea of going where no one has gone before. The greatest science that has come out of the Hubble telescope was when the director pointed it to a place where nothing was known to exist and just kept it there for 2 weeks. And the Hubble Deep Field came out of that. I mean, they discovered that there's a lot more galaxies in the universe than ever before, and a lot more scientific research and scientific discoveries came out of that one image.
We know about dark matter, or what there is to know, through the experiments and the research that's still going on, but there's also dark energy.
Yeah.
How do the two differ, or are they connected in some way?
We don't know if they're connected. There are theorists who are trying to connect the two, but in terms of the observations, they're very different. So the dark matter has an influence on other normal matter gravitationally. So we infer it's there because its gravitational force can be seen by the action of the motion of the normal things like the stars and the gas. The dark energy, so far as we can tell, is very smooth. Its distribution in the universe appears to be very smooth, and the consequences of dark energy are that the universe, instead of decelerating as a function of time in its expansion, so that, you know, you've probably heard of the Big Bang, everything is moving apart with time, but how fast it's moving apart is slowing down as a function of time. It's decelerating, and that's because of the gravitational pull of everything in the universe. It's slowing down the expansion,
Gotcha.
you know, as a function of time. What we've observed is that in the last, maybe 5-6 billion years, it's gone from decelerating to accelerating. It's, a lot of people in the popular literature refer to it like an anti-gravity. Instead of everything being pulled together, suddenly it's being pushed out at a faster and faster rate. And Einstein's equations actually can be used to understand this at some level. If dark energy is of a particular type, then Einstein's equations can explain it as something called the cosmological constant. But that's all we know about it. We know that it's causing the universe to go through an accelerating period in its expansion. What is it? Is it a new kind of energy? You know, I tell as a joke to some of my students that these names, dark matter and dark energy, it's not just that the stuff is dark and we don't see it, and so we don't know what it is, but it also refers to the darkness in ourselves, in the sense that we're ignorant, we're in the dark about what these things are.
Sure.
And so they appear, you know, to be completely different things. But there are people who are trying to connect the two, and we just don't know. The dark energy is a tremendous mystery. We have very few ideas, I think, as to what it is.
So much of this type of research is done on what's not known. You have to be a lover of mystery to pursue that in many ways. When did you become interested in this kind of astronomy and physics?
I went to school very early. I was about 16 when I went to college. And I started research at a very, very young age. I was in a chemistry major.
Wow.
And got involved into in a group that was doing theoretical chemistry, so quantum mechanics and things like
At
that.
16? Wow.
At 16, 17. So I was 16, I was an undergraduate. At 17, I started research, and I just completely was absorbed by it. And I think maybe burnt out a little bit.
I was going to say, maybe a little burned out at that age.
And burnt out, a little bit, disillusioned as to what I thought I wanted to do. And I took some time off, and this was in Boston, and got involved in a couple of startup companies and had lots and lots of fun. But I did a lot of reading along the way. And what I found that the part about chemistry that I liked a lot was, the quantum mechanics, and read a lot about quantum mechanics. And like many people in my generation, I was inspired by Richard Feynman, who was, making a lot of popular works at the time, Nova, and a lot of popular books, and Bohr and Heisenberg and all of these things. And I thought it'd be wonderful to actually participate in some of this. Would it be possible for me to go back to school to learn, physics? And that's kind of when it all started. I went back to school, and I didn't go back to school as an undergraduate. I just started a PhD. And I was very fortunate to be able to do it in physics.
And now I would think that some of the tools you're using have got to be kind of exciting. Talk to me about that.
The hypotheses for dark matter, the standard vanilla hypothesis, is that it's a new fundamental particle. You've probably heard about the Higgs being discovered recently. This new particle that people think is dark matter is a very generic name. It's called a weakly interacting massive particle, or the WIMP.
The WIMP, I like the name for it, because you remember that.
Yeah, you remember that. And so they're trying to create it at the LHC. That's one of the goals, one of the major goals of the Large Hadronic Collider, which is this accelerator that may have discovered the Higgs. And it goes back to Einstein's equation of E is equal to mc squared. You create enough energy to produce particles of a mass mc squared, for instance. Maybe they created the Higgs that way, and they're going to confirm whether it is the Higgs. They also want to produce the WIMP in the same way. That's one tool, if you will, to find out what dark matter is, to produce it. The other is that the galaxy is full of dark matter. So these particles are moving right through us as we speak. And every second through my hand, there's something like 10 billion of these particles passing through if they had a particular mass. They have a very, very weak interaction, and the probability that they will actually hit an atom in my hand is very, very, very small. So they're there. They're in this room all the time. So instead of creating them, I might just build an experiment to actually detect that. And that's the kind of research that I do. We're actually looking, it's called a direct search for dark matter. It's all already there. It's passing through us all the time. So let's make a detector through which this dark matter will pass. Once in a while, it'll give you an interaction. And it's a very characteristic kind of an interaction. So we look for that. And while we're looking for it, there's a lot of ordinary stuff happening inside our detector due to cosmic radiation and radioactivity and so forth. And on the surface of the Earth, that stuff dominates. So what we do is we take our experiments deep underground, like a mile underground if we're lucky.
There's a mine, isn't there?
There's a mine called the Bowlby Mine in the United Kingdom. And it's part of the mine is under the North Sea. And we put our detectors deep underground there where it's much quieter.
And so if you do find it, what then do you do with it?
Where we are right now, at least me as a scientist looking for this stuff, is just would be wonderful to get some hints as to what it is. And we're driven just by that question, we started this conversation with, which is what is out there. And, my nature is the kind where I think I would leave it to others to maybe think how you would use it if that happens one day. It's very difficult to say.
Yeah, well, it's kind of like the space is your oyster. I guess if you keep moving in that direction, at least your research will lead to something else, and who knows when that timeline will actually kick in. But thank you so much.
Sure. Welcome.
Joining me now is Dr. Monica Serino. Monica, what is it about the classic stories that bear repeating and repeating and repeating?
The classics are familiar to most audiences, whether or not students take them in school or become fans on their own. I think there's something about us as Americans and our American culture that we relate back to the Greeks and Romans in ways that are cultural, are political, sexual, all kinds of different ways. So there's a familiarity about it, but also there's a distancing that you can put it back off, onto this earlier culture, very earlier, 2,000, 3,000 years ago. So there's a safe distance to talk about our modern issues of, politics, social issues, economic issues, relationship issues, gender issues. And we talk about it using these sort of familiar people, these characters from Greek mythology or Roman history, and yet they're distant enough for us to be able to work out these problems and of course be entertained while we're doing it. So it's become a really, really commercially and critically provocative field, I think, for filmmakers and television producers today.
Kind of a reference point too. It's like, this is how it used to be, and so this is how we've now evolved.
The thing that's interesting is that how they used to do it is pretty much how we still do it, right? If you take away, machines and digital capabilities, pretty much all the technologies we have today, the ancient Romans had. Running water, agriculture, roads, aqueducts, things like that. So because the wealth of the material, the literary and artistic material that they've left us is so brilliant and sublime, excuse my bias, because it is just so wonderful, we look at them as a very sophisticated culture, obviously. And in fact, many things that we've done in this country, our forefathers and foremothers created this country based on Greco-Roman ideals, right? And modeled Washington, D.C. after ancient Rome and all that.
What do you think filmmakers are saying about contemporary societies by, retelling these stories?
I think the reason that filmmakers want to use the classical world is because the contemporary issues today are they're so fraught, right? I don't think it's going out on a limb to say that we live in trying times,
it's
right?
Complicated.
Yeah, it's very complicated. And I think that what they're saying about contemporary society is that there are political intrigues that are very, very complicated and very intense. There are gender, race, class issues, hierarchies that continue to just, knock us over the head. Can't we get this sorted out? Why do we have to have this argument again and again and again? There are issues of culture and who has access to culture, who has access to the good life. All things that we know that the ancient authors and ancient thinkers and writers and artists talked about. And so putting it back onto that environment allows us to sort of say maybe some not so pleasant things about our modern society and work them out, of course, in costume and on beautiful sets, right? With gorgeous actors playing all the roles. I'm Cleopatra or whatever, right? So, so it's a win-win, right? You get to have your art make commentary about modern society, but you also get to make beautiful art, with beautiful people, and hopefully make some money along the way.
What do you think are some of the contrasts that stand out to you in the the modern versus the classic perspective?
When you do have a TV series or a film like 300 or Troy or Alexander, you obviously can't recreate the thoughts of an ancient character. Sure. You can represent the story and who won the battle and so forth and try and be authentic that way. In terms of gender relationships and the representation of women, it seems that modern filmmakers and TV producers have put a little bit more freedom and sort of progressive ideas onto the way, especially female characters handle themselves. I think in general there's a heavier reliance on psychological motivations for characters that we just don't know, So I don't
conjecture.
Yeah,
it's entertaining, but I would agree with that.
Yeah.
Did they have those liberties to do that? And of course, in today's film world, they do.
And in fact, going back to why ancient Rome is such a great location for talking about the modern world, there isn't any time in the history of the planet up until, I don't know, the 1960s in America where women were as free as in ancient Rome. Toward the end of the Republic, right around the big, change of BC to AD, you might say, was about the time when women, especially women of a certain means, more elite women, had an incredible amount of freedom. So when they portray these women on TV or in a film, it comes closer to our time. Do you know what I mean?
Oh, no, absolutely. It makes for better TV,
absolutely.
if you will.
You can relate to those people.
Exactly, yes. So what do you think about violence and the portrayal of women now? Is it getting better, for lack of a good word to describe it? Or, I mean, it seems like there's just as much, if not more.
Yeah, exactly. I mean, as you know, movies in general are just a lot more violent, and television shows too, especially on cable, they can get away with more. What's interesting when you talk about the classical world, the Greeks and the Romans being represented on screen, is that it seems to me, whereas the violence quotient is being ratcheted up, just like in all televisual and cinematic media, it seems to me that there's some of this stuff is being, in fact, made for women. There just are a lot of sexy male bodies in these shows now. And I think we're seeing a real sea change. And again, I'm very excited about this because entertainers, creative artists are using the classical world to make a big change in the way we look at contemporary media. And I think that's by making it for us, Augusta. It's for women now. We get to see.
We're the targeted audience.
Yeah, we're the targeted audience.
What inspired you? I mean, you really, what do you find, I think I can tell what you find interesting about it, but there's obviously something there that you keep wanting to find out.
I guess when I started my college career as a journalism major, because I wanted to do what you do, in fact, interview people and sort of get into media and communications. And at the same time, I started reading the classics. And I just fell in love. What can you say? It was love, and you do stupid things for love. And so, 10 years later.
Career isn't a stupid thing.
Yeah, exactly. 10 years later, I found myself a professor at a research institution trying to figure out how to make Greek mythology and Roman history interesting to students. So, I went back to my first love and said, well, I can show, and we had nothing back then. There were no clips, there was no internet, there was, you had to literally have a videotape or something, it was just, it was the dark ages, well, I have friends who used film reels, so I feel, much more younger than they are. So, I just started employing that in my teaching in a very small way. And it got me to thinking, as most professors are trained to do, why are these people making these films that I'm showing in class, or this comedy routine from Saturday Night Live or whatever? Why is this familiar to audiences in America or whatever? So I started thinking about that, and then it became this huge sort of research interest of mine. So I don't know, that it's sort of a confluence of my interest in popular culture and ancient culture, which sounds crazy, but there you have it. It's love.
It makes me want to take your class.
Oh, thank you.
Thank you so much
Thank you.
for interviewing today. That was great.
Great, thank you.
Global warming is going to shake up bird distributions in all kinds of ways that are difficult to predict. How hummingbirds are going to be affected is to look at how they already have been affected by the first approximately 1 degree of warming that's already happened. We've got a couple species here in North America that have made radical shifts in their distributions. First, the Anna's hummingbird in California has expanded from Southern California outward to British Columbia in the north, and Mexico, Arizona, and New Mexico in the east. Perhaps even more dramatic, since the late 1970s, we've seen several species of North American hummingbirds expand their wintering ranges to include the southeastern United States, in addition to their traditional wintering grounds in southern Mexico and Central America. So we've got species like the Rufous hummingbird from the Pacific Northwest, the broad-tailed and calliope hummingbird from the Rocky Mountains, and the ruby-throated hummingbird from the northeastern United States, all regularly winter along the Gulf Coast between Texas and Florida, and even up as far north as North Carolina. Amazingly, last January, in the middle of typical Chicago winter, a Rufous hummingbird showed up at a feeder in a Chicago neighborhood. So there are radical changes going on in the migratory routes and wintering ranges of these hummingbirds in response to warming, and probably also to the expanded availability of ornamental plantings and hummingbird feeders. Now let's look at these hummingbirds from the standpoint of their evolutionary relationships. We've sequenced DNA from these museum specimens so that we can tell what the branching pattern is of the evolutionary lineages that go back perhaps 20 or 30 million years. And what this shows us is that the high altitude distribution has evolved multiple times in different hummingbird lineages. Our research here at the Museum of Southwestern Biology has focused on the ways that they are adapted to breathing when oxygen is reduced in density. Here in Albuquerque, we've got two hummingbird species that breed, the black-chinned hummingbird and the broad-tailed hummingbird. The black-chinned hummingbird is the hummingbird of the valleys. The broad-tailed hummingbird is restricted to the mountains. As global warming proceeds, we expect the black-chinned hummingbirds to be moving up to higher altitudes. And because they're competitively dominant over the broad-tailed, they could be displacing them. That phenomenon of upslope shifts in distribution is important because as we look from our hummingbirds here in Albuquerque to diverse hummingbirds in Peru, we should expect to see the same things happening. If we go to the Peruvian Andes, they've got 125 species of hummingbirds, and just about all of them have restricted elevational ranges. Over the coming decades with warming, we're expecting that temperatures and vegetation zones should shift upslope by about 300 to maybe 700 meters. We've seen massive changes in hummingbird distributions here in North America over the latter half of the 20th century and the first decade of the 21st century.
Do you have a question for our experts? Please email us your viewer questions and comments to askconnect@newmexicopbs.org. Thank you for watching. Production support provided by the University of New Mexico.